So right now we're going to go ahead and talk about how to find the angular momentum of a point particle. So let's say you have a ball of mass m on a massless string. So I'm going to go ahead and draw that. So we have a ball of mass m on a massless string rotating in a circle of radius r. What is its angular momentum? The tangential speed is v of this object as it's rotating. Okay, so we know that the formula for angular momentum is L equals I omega. Let's go ahead and see if we can come up with a new formula for angular momentum if we're dealing with point masses or point particles. Okay, so I, for this case, for a point mass, is going to be mr squared. We want to figure out how do we relate together v and omega. Let's see if we can get something dealing with v in there. So we know v is equal to omega r. So let's see, we solve for omega. That is going to be v over r. Cool. Ooh, fun. And r cancels out, and we're left with mrv. So this right here is an equation that will work for point particles only. So this will not work for all objects, but for point particles, it will work, and it is a great, nice little shortcut if you're given a tangential speed. I encourage you to use that when you're finding the angular momentum of something. So let's think about, and we know that's the mass, v is the tangential velocity. Let's talk about what r is. So r is the radius of the particle if it is moving in a circle. So sometimes we won't deal with things where it's moving in a circle. Sometimes we'll deal with a situation like this, where we have something has a tangential velocity with some mass, and there's a pivot point, let's say right here. What I'm going to do is I'm going to draw a line parallel to the velocity, great, that goes through the pivot point. So the r is then going to be the line that is perpendicular to the line that is the parallel velocity line and the line that goes through the pivot point. So again, the r is perpendicular to the velocity vector. And if you look at the circle thing too, the r and v are perpendicular as well. So that's another way to look at it. Awesome. So let's go ahead and solve an example problem together. So let's look at this one. So we have a 2 kilogram rock. And I encourage you to try this one yourself and then check back in on the video. So it's a horizontal velocity of 12 meters per second. So that is a linear velocity v, since the units are meters per second, when it is at point P in the figure below. At that instant, what is its angular momentum relative to point O? Okay, let's go ahead and look at this. So angular momentum, this is a point particle, so we can use mvr, and that'll just be a nice little shortcut. You could also use the regular equation for angular momentum, I omega, but let's go ahead and use mvr just to, because mvr is going to be easier in this case. So let's see, the mass is 2, the velocity is 12. Okay, now we need the radius. Again, the radius is going to be perpendicular to the velocity and perpendicular to the line parallel to that velocity. So that is going to be, this line right here is your r. Ooh, hoo, hoo. How do we find that? That is going to be some fun tricks. So r is going to be, let's see, that's opposite over hypotenuse. So r is going to be 8 sine of 36.9, which I get when I plug that in, I get about 4.8. Cool. So let's go ahead and plug that in. So that's going to be 4.8 we can plug in. And then I have 115 kilogram meters squared per second. Awesome. Thanks so much for watching. Again, this was all for the angular momentum of a point particle. If you want a video on general angular momentum, I have another one in the video archives for that.